Space, a realm of undiscovered wonders, brimming with the solutions waiting to be unraveled. It's not just a place for exploration, but also a realm where we seek answers about existence and our role in the universe. Imagine standing at the edge of what we know, peering into the endless expanse of space and embarking on a journey to uncover its secrets. This is our quest. In this documentary, we will delve into the depths of space, navigating through billions of galaxies, each containing countless stars and planets. Our goal is not just to map out celestial bodies, but also to tackle the profound questions that have fascinated humanity for ages. What lies beyond the observable universe? Are we alone in this vast expanse, or is there life waiting to be discovered? The universe encompasses everything we know: space, time, matter, and energy. It began approximately 13.8 billion years ago with the Big Bang, a moment when the universe exploded into existence from an incredibly dense point called a singularity. One of the most fascinating aspects of the universe is its composition. Only about 5% of it is made up of ordinary matter, like stars and galaxies. The remaining 95% is composed of dark matter and dark energy, enigmatic forces that don't emit light or energy but play crucial roles in shaping the cosmos. Dark matter, accounting for 27%, holds galaxies together like cosmic glue, while dark energy, making up 68%, drives the universe's expansion at an accelerating rate, an astounding discovery that reshaped our understanding of the cosmos and earned a Nobel Prize in Physics in 2011. Exploring the universe isn't just about understanding stars and planets. It's a journey that delves deep into the very fabric of reality and our place in it. Both philosophers and scientists ponder questions about where the universe came from, what will happen to it in the end, and the rules that govern its behavior. This pursuit of knowledge challenges our understanding of existence itself, leading us to contemplate concepts like the multiverse theory, which suggests that our universe might be just one of many. Determining the age of the universe is a tale spanning centuries of observations and scientific breakthroughs. It all began with ancient civilizations gazing at the stars and wondering about their origins. But the real journey toward understanding the universe's age began in the 20th century, driven by key discoveries in physics and astronomy. A pivotal moment came in 1929 when Edwin Hubble noticed that galaxies were moving away from us, indicating that the universe is expanding. This observation laid the groundwork for the Big Bang theory, the leading explanation for how the universe began. Astronomers determined the rate at which the universe is expanding, called the Hubble constant, by observing how quickly galaxies move away from us. Initially, estimates of this constant hinted at a younger universe. But as technology improved, especially with tools like the Hubble Space Telescope and later the Planck satellite, our understanding became more precise. These advancements allowed for better examination of the cosmic microwave background radiation, giving us clearer insights into the universe's early stages and refining the Hubble constant to a more accurate value. Another way to gauge the universe's age involves studying the life cycles of stars. By observing the oldest stars within dense groups called globular clusters, astronomers can estimate the minimum age of the universe. These ancient stars, among the first to form after the Big Bang, act as a sort of stellar clock for cosmic history. The oldest of them appear to be nearly as old as the universe itself, suggesting a lower limit of around 13 billion years for the universe's age. As we deepen our exploration of the cosmos, the concept of the observable universe becomes intriguing. It builds upon our understanding of the universe's vastness and age. The observable universe refers to the part of the entire universe visible or detectable from Earth. However, it's limited by the speed of light and the age of the universe. Since light travels at a finite speed, it takes time for light from distant objects to reach us. As a result, the observable universe forms a sphere with Earth at its center, extending outward to a radius of about 46.5 billion light-years. The observable universe extends to the farthest distance from which light has had time to reach us since the universe began, around 13.8 billion years ago. It's essential to distinguish between the observable universe, which we can see, and the entire universe, which encompasses all of space, much of which remains beyond our current observational abilities. The actual size of the entire universe is still unknown. It could be infinitely large or structured in a way that challenges our understanding of geometry. If you're still watching, please like the video and turn on notifications for the channel so you don't miss our weekly documentaries. Within the observable universe, there are an estimated 2 trillion galaxies, each containing millions to trillions of stars, along with numerous planets, asteroids, and comets. This vast count comes from extensive sky surveys and observations made by powerful telescopes like the Hubble Space Telescope. By peering deep into space and time, these observations not only expand our comprehension of the universe's vastness, but also shed light on how cosmic structures formed and evolved over time. Exploring the observable universe also involves grappling with concepts like cosmic inflation, a theory proposing that the universe experienced rapid exponential expansion in its earliest moments. This expansion stretched the very fabric of space, contributing to the immense distances between galaxies observed today. It's a concept that merges ideas from cosmology and theoretical physics, offering explanations for phenomena like the uniformity of the cosmic microwave background radiation and the distribution of galaxies throughout the cosmos. When we explore the observable universe, we come face to face with the limits of our technology and the laws of physics. Some parts of space are beyond our sight because the light from those areas hasn't reached us yet. But thanks to advances in telescope technology and observation methods, we are continually expanding our understanding of the universe, learning more about its structure, history, and the rules that govern it. But how exactly do we observe this vast expanse that spans billions of light years? Observing the universe involves using various tools and techniques, each aimed at capturing different aspects of cosmic phenomena. Telescopes lie at the heart of this exploration. They've evolved from the basic optical telescopes used by Galileo to today's advanced observatories capable of detecting various forms of electromagnetic radiation, like radio waves, infrared, ultraviolet, X-rays, and gamma rays, not just visible light. Optical telescopes, which gather visible light, were crucial in our initial exploration of space. They've allowed us to see stars, galaxies, and nebulae within the observable universe. But to fully grasp the universe's complexity, we've had to expand beyond what's visible. For instance, radio telescopes can pick up radio waves emitted by distant cosmic objects. These instruments have unveiled phenomena invisible to optical telescopes, like the cosmic microwave background radiation, a signal from the universe's early days, offering key evidence for the Big Bang theory. Infrared astronomy gives us a way to see celestial objects that are hidden by dust clouds, which visible light can't pass through. It's shown us new stars forming and galaxies in the distant universe that we couldn't see with regular light. Similarly, X-ray and gamma-ray astronomy help us study high-energy events like those near black holes and neutron stars, giving us insights into the most intense events in space. The development of space-based telescopes has been a big step forward in how we observe the universe. Tools like the Hubble Space Telescope, positioned outside Earth's atmosphere, provide clear, distortion-free images, offering us a detailed view of the cosmos. Its successor, the James Webb Space Telescope, focuses on infrared astronomy, aiming to study the earliest galaxies and delve into the mysteries of star and planet formation. Our exploration of the universe goes beyond just electromagnetic radiation. Neutrino observatories, for instance, detect almost weightless particles that give us insights into solar processes and supernova. Meanwhile, gravitational wave observatories like LIGO detect ripples in the fabric of spacetime, caused by massive events like black hole or neutron star collisions. This approach offers a unique way to study phenomena that emit little or no light. Our journey of observing the universe is continually evolving, driven by both technological advancements and theoretical progress. But why can't we see beyond the observable universe? This question dives into fundamental aspects of physics and the nature of the cosmos itself. The observable universe is defined by the farthest distance from which light has had time to reach us since the universe began around 13.8 billion years ago. This limit isn't physical, but is determined by the finite speed of light and the age of the universe. Light travels at a constant speed of about 299,792 kilometers per second in a vacuum, setting a limit on how far we can see. Given the universe's age, the farthest light we can observe has traveled from a distance corresponding to the universe's age, allowing us to glimpse back to the cosmic light horizon. The horizon of the observable universe, located approximately 46.5 billion light-years away, is defined by the universe's expansion since the Big Bang. Beyond this boundary lies the unobservable universe, hidden because light from those areas hasn't had enough time to reach us yet. As the universe expands, driven by dark energy, galaxies move away from us at increasing speeds with distance. Eventually, at a point called the Hubble length, these speeds surpass the speed of light. Quick reminder to subscribe if you haven't already, so you can keep up with our future astronomy documentaries. Thank you so much. L. This doesn't break Einstein's theory of relativity, which says objects in space can't move faster than light because it's the space itself that's expanding. The idea of the observable universe connects to the theory of cosmic inflation, proposing that the universe rapidly expanded right after the Big Bang. This stretched space so much that some regions are now too distant for their light to ever reach us, limiting what we can see. This limit isn't just about distance, it's also about time. When we look out into space, we're also looking back in time. The farther we look, the older the light we see. Eventually, we reach the cosmic microwave background radiation, the glow left over from the Big Bang, representing the earliest observable light. Beyond this lies the cosmic dark ages, a time before stars existed. To explore these distant mysteries, astronomers use advanced tools to observe far-off objects. These tools, each serving a specific purpose, help us explore the vastness of space and time, offering detailed glimpses into the cosmos. Among these tools, telescopes stand out, coming in different types, tailored to different light wavelengths. Optical telescopes, for instance, gather visible light and have been fundamental in astronomy for centuries. They range from ground-based observatories to space telescopes like the Hubble Space Telescope, allowing us to observe planets, stars, galaxies, and nebulae within the visible spectrum. But the universe doesn't just emit visible light, it sends out information across a wide range of wavelengths, much of which we can't see with our eyes alone. To capture this data, astronomers turn to radio telescopes, such as the Very Large Array in New Mexico or the Atacama Large Millimeter Sub-Millimeter Array in Chile. These telescopes can peer into the cold, dark regions of space like gas and dust clouds where new stars form, or even detect remnants from the Big Bang. Infrared telescopes like the Spitzer Space Telescope cut through cosmic dust to uncover hidden star clusters and galaxies, shedding light on star formation and the early universe. Conversely, X-ray and gamma-ray observatories, like the Chandra X-ray Observatory and the Fermi Gamma-ray Space Telescope, delve into the universe's most energetic occurrences, such as black holes, neutron stars, and supernovae. They unveil the mechanisms driving these intense events. In addition to electromagnetic radiation, recent progress has introduced new tools for observing the cosmos. Gravitational wave detectors such as LIGO and Virgo have revolutionized our view of the universe by capturing ripples in spacetime created by colossal events like black hole or neutron star mergers. This breakthrough has ushered in the era of multi-messenger astronomy, where gravitational waves and electromagnetic signals are combined to give us a fuller understanding of cosmic happenings. Spacecraft and probes, such as the Voyager probes, the New Horizons mission to Pluto, and the Mars rovers, expand our ability to explore, offering close-up views of planets, moons, and other celestial bodies both in and beyond our solar system. Each of these tools plays a crucial role in uncovering the mysteries of the universe. By combining observations from different parts of the electromagnetic spectrum with insights gained from gravitational waves and neutrinos, astronomers can build a more complete understanding of the universe's makeup, evolution, and the laws that govern it. Our understanding of the universe has evolved significantly over the centuries, progressing from ancient beliefs to the data-driven perspective we have today. This journey of discovery reflects humanity's ongoing desire to grasp the vastness of space and our position within it. In ancient times, cultures worldwide blended mythology with early astronomical observations to conceive the universe. For instance, the Greeks envisioned the heavens as a crystal sphere encasing the Earth with stars affixed to it. This geocentric view, placing Earth at the universe's center, prevailed in Western thought until the Renaissance. The 16th and 17th centuries saw a pivotal change with the work of Nicholas Copernicus, who proposed a heliocentric model positioning the Sun rather than the Earth at the universe's center. This revolutionary idea laid the groundwork for further scientific advancements. Johannes Kepler and Galileo Galilei played crucial roles in shaping modern astronomy by challenging long-held beliefs with careful observations and mathematical principles. They provided strong evidence for heliocentrism, the idea that the Sun, not the Earth, sits at the center of the solar system. Galileo's use of the newly invented telescope in the 17th century led to groundbreaking discoveries, such as Jupiter's moons and Venus's phases, which undermined the geocentric model that had dominated for centuries. This period marked a shift from philosophy-driven views of the cosmos to ones based on empirical evidence and observation as telescopic technology improved. In the 18th and 19th centuries, astronomers discovered new planets within our solar system. The 20th century brought the revelation that galaxies exist beyond the Milky Way, with Edwin Hubble's work demonstrating an expanding universe. This supported the Big Bang theory, suggesting the universe had a definite beginning. In the latter half of the 20th century and into the 21st, our understanding of the universe expanded significantly with space telescopes and advanced ground-based observatories. These tools help detect exoplanets around distant stars, study the cosmic microwave background radiation, a remnant of the Big Bang, and map dark matter and dark energy, which make up most of the universe's mass energy content. Today, our view of the universe is shaped by the Lambda CDM model, which describes a cosmos largely governed by dark energy and dark matter, with ordinary matter, like stars and planets, playing a smaller role. This model, backed by observations from tools like the Hubble Space Telescope and the Large Hadron Collider, describes a universe that's 13.8 billion years old, always expanding and filled with galaxies spread across vast distances. The journey of understanding the universe reflects human curiosity and our relentless pursuit of knowledge. It's a shift from old Earth-centered views to realizing Earth is just a tiny part of a vast, expanding cosmos. In exploring space, the term light year is crucial for understanding the vast distances between celestial bodies. A light year isn't a measure of time, but of distance. It's the distance light travels in one Earth year at a constant speed of about 299,792 kilometers per second in space. That's roughly 9.46 trillion kilometers, or about 5.88 trillion miles. Using light years helps astronomers and cosmologists explain the immense gaps between stars, galaxies, and other cosmic features in a way that's easier to grasp. Using light years as a unit of distance is important for a few reasons. Firstly, it gives us a standard way to talk about the huge scales of the universe that we can understand. For example, when we say a star is 4.37 light years away, like Proxima Centauri, the nearest star to the Sun, we know that the light we see from it today began its journey to us 4.37 years ago. This connection between time and distance helps us appreciate how dynamic and vast the universe truly is. Using light years as a unit of measurement aligns with the core principles of physics and astronomy. Because the speed of light is constant, a key aspect of Albert Einstein's theory of relativity, it gives us a reliable way to measure distances in space. This consistency means that the light year is a universal measurement relevant across various observations and theories in astrophysics and cosmology. Light years also make communication easier among scientists and the public. For example, when astronomers discover a galaxy 100 million light-years away, it immediately conveys the vast distances and timeframes involved in the universe. It helps us understand not just how far apart cosmic objects are, but also the timescales involved, as observing space is like traveling back in time due to the light's journey across these immense distances. The formation and changes of galaxies are essential processes that show how the universe evolves over billions of years. This story starts shortly after the Big Bang, the explosive event that gave birth to the universe about 13.8 billion years ago. After the Big Bang, the universe was a hot, dense mix of particles and energy. As it expanded and cooled, matter began coming together under gravity's influence, leading to the formation of galaxies. The first galaxies took shape from small differences in the density of the universe's early matter. These slight variations, like tiny wrinkles in space, were boosted by the gravitational pull of dark matter, drawing in ordinary matter. Within these dark matter clouds, gas cooled and collapsed, breaking into smaller clumps where stars could form. This process gave rise to the first stars and proto-galaxies just a few 100 million years after the Big Bang, in a period known as the cosmic dawn. Galaxies change over time through various processes. One major factor is star formation. Dense areas of gas and dust within galaxies collapse under gravity's pull, triggering nuclear fusion in their cores and creating new stars. The life cycles of these stars, from their births to their explosive deaths as supernovae, release energy and heavy elements back into the galaxy, fueling more star formation and enriching the galaxy's chemistry. Another important process in galactic evolution is galaxy mergers. Gravity pulls galaxies together, leading to collisions and mergers that can drastically alter their shapes. These cosmic crashes can spark intense bursts of star formation, transform spiral galaxies into elliptical ones, and feed supermassive black holes at their centers. Even our own Milky Way is heading for a collision with the Andromeda Galaxy in about 4 billion years, showing how galaxies are always changing. Throughout their lifetimes, galaxies undergo different changes influenced by their surroundings and interactions. Some galaxies collide and merge, while others lose gas to neighboring galaxies. Many galaxies evolve independently, gradually turning their gas into stars as time passes. The rate at which stars form, and the impact of central black holes, which can either trigger star formation or suppress it, play significant roles in determining a galaxy's appearance and future. The study of galaxy formation and evolution is an active area of research, using observations from telescopes and simulations on powerful computers. These studies aim to understand the complex journey of galaxies, from their beginnings in the smooth universe of the Big Bang to the diverse structures we see today. Within our universe, there are massive structures called superclusters, which showcase the vastness and complexity of space. These superclusters are made up of groups of galaxies and galaxy clusters connected by dark matter filaments spanning millions of light years. Superclusters are important not only for their size, but also for what they reveal about the universe's underlying structure, the distribution of matter, and the gravitational forces shaping space. They form where cosmic web filaments intersect, forming networks of dark matter that influence how galaxies and galaxy clusters are spread out in space. The web-like structure of superclusters is a result of small variations in the early universe, amplified over billions of years by dark matter's gravitational pull. Studying superclusters allows astronomers to track how these structures evolved from the universe's earliest days, shedding light on dark matter and cosmic expansion dynamics. One well-known supercluster is Laniakea, which includes the Milky Way among its tens of thousands of member galaxies. Spanning about 500 million light-years, Laniakea's discovery highlighted the interconnectedness of galaxies in the universe, emphasizing our position within these immense cosmic structures. Galaxies flow towards denser regions within superclusters due to gravity, showcasing the dynamic nature of space, with galaxies constantly moving and interacting within this vast framework. Superclusters are also crucial in cosmology, the study of the universe's origin, structure, evolution, and future. The distribution and mass of superclusters affect the universe's overall shape and expansion rate, crucial for understanding cosmological theories. Observing superclusters and their arrangement helps refine measurements of the universe's expansion, providing evidence for dark energy's existence, the mysterious force speeding up cosmic expansion. Additionally, superclusters offer insights into galaxy evolution on the largest scales. Superclusters offer different environments for galaxies, ranging from dense centers filled with galaxy clusters to more solitary galaxies on the outskirts. These varying conditions affect how stars form, how galaxies interact, and even how supermassive black holes grow. Studying these environments helps astronomers learn how galaxies change over time and how their surroundings shape their evolution. The cosmic web is a term describing the vast and intricate network of galaxies and galaxy clusters. It's like a giant spider web spread across space, with galaxies and clusters connected by threads of dark matter. In between these structures are huge voids where there are very few galaxies. This cosmic web is the largest structure in the universe, formed because matter wasn't evenly spread out after the Big Bang. Over billions of years, gravity, especially from dark matter, pulled matter together, forming this web-like structure. Understanding the cosmic web starts from the early universe, when tiny differences in density began to shape its structure just after the Big Bang. As the universe expanded, small areas with slightly more matter, called overdensities, grew bigger due to the pull of dark matter's gravity. Around these overdensities, gas and dust gathered, eventually forming stars, galaxies, and clusters of galaxies. On the other hand, areas with less matter became what we now call cosmic voids, huge empty spaces scattered across the universe. The cosmic web's shape is mostly shaped by dark matter, a mysterious substance that makes up about 27% of the universe's total mass and energy. Even though we can't see dark matter directly, we know it's there because of how it affects visible matter and the structure of the universe through gravity. Dark matter's gravity pulled matter together, creating the dense areas that became galaxies and galaxy clusters while leaving behind the empty voids. Surveys of galaxies, like the Sloan Digital Sky Survey, have given us detailed maps showing how galaxies are spread throughout the universe. These surveys reveal that galaxies aren't randomly scattered. Instead, they form long filaments stretching across millions of light years. These filaments surround vast empty voids and come together at massive hubs where galaxy clusters are found. The cosmic web isn't just a leftover structure from the past, it's always changing and evolving. Galaxies move along these cosmic highways, drawn toward the massive galaxy clusters by their strong gravity. This movement, happening over incredibly long periods, shows how the universe continues to grow and form structures thanks to the pull of dark matter and gravity. Studying the cosmic web is super important for a bunch of reasons. It helps us understand how dark matter shapes the universe over time, how galaxies form and grow, and how stuff is spread out in space. Plus, figuring out the cosmic web helps astronomers fine-tune their ideas about how the universe works, including understanding dark energy, the mysterious force making the universe expand faster. Black holes are like the universe's enigmatic gatekeepers sitting at the heart of many galaxies. They're so dense and have such strong gravity that even light can't escape their grip. These cosmic giants have a huge influence on how galaxies, stars, and even matter across the cosmic web are arranged and behave. Black holes are super interesting because they're not just mysterious. They have a huge impact on the whole universe. Most big galaxies, like our Milky Way, have supermassive black holes at their centers. These monsters are millions to billions of times heavier than the Sun and aren't just leftovers from the universe's wild past. They're active players in how galaxies work. They have a big effect on their galaxies, controlling how many stars are born and shaping how galaxies change over time with all the energy they let out. When galaxies crash into each other, their central black holes do too, releasing tons of energy and possibly shaping how the universe looks. Black holes also help make up the cosmic web by powering things called quasars and active galactic nuclei, AGN, which are some of the brightest things in the universe. These super bright objects can be seen from really far away and light up the space between galaxies, affecting how they grow and change along the cosmic web's long strands. The energy from AGN can stop stars from forming in galaxies, changing how the universe looks on a big scale. Plus, when black holes smash into each other, they send out ripples in space called gravitational waves. We detected these for the first time in 2015, and they're giving us a whole new way to understand the universe, including how many black holes are out there and how they've affected how the universe has changed over time. Gravitational wave astronomy could help us figure out where black holes are scattered throughout the cosmic web, giving us a clearer picture of how they fit into the universe's design. Understanding black holes also ties into big questions about how the universe works. Theories like string theory and loop quantum gravity, which try to merge quantum mechanics with general relativity, often use black holes to test out new ideas about space, gravity, and what's going to happen to the universe in the end. One of the biggest mysteries is the information paradox, which asks how information stays around in a universe with black holes. Figuring this out could be a key to unlocking the universe's most basic rules. Black holes aren't just weird space things. They're actually super important for how the universe is set up and how it changes over time. They help keep galaxies in place, shape the cosmic web, and give us hints about how nature's forces work. Studying black holes doesn't just challenge what we think about space and time. It also shows us how everything in the universe is connected, from tiny particles to the biggest stuff out there. Now, let's chat about voids. Voids might seem like just empty spaces in space, but they're actually crucial for understanding how the universe has grown and changed over time. They're kind of like the blank spots in a painting, showing us where galaxies aren't, just as much as clusters and superclusters show us where they are. Voids back up ideas about cosmic inflation and dark matter, suggesting that way back in the beginning, little quantum jitters led to how matter is spread out across the universe today. Despite their name, voids aren't completely empty. They do have some galaxies, but not nearly as many as other parts of the universe. These galaxies tend to be smaller, less hefty, and not as bright as the ones you find in places like galaxy clusters. Looking at these lonely galaxies can help us learn a lot about how galaxies form and change, without all the complicated gravitational stuff happening in busier areas. We've been able to find and map these voids thanks to really big surveys that track where galaxies are all across the sky. These surveys show us that the universe has this web-like structure made up of filaments, like the strands in a spider's web, and huge empty spaces in between called voids. These voids can be all kinds of shapes and sizes, with the biggest one we know about, the Bouteille's void, stretching about 330 million light-years across. Voids aren't just sitting still, though. They're growing as the universe itself expands, pushed along by dark energy, which is this mysterious force that pushes things away. Studying voids helps us understand how the universe is growing and changing over time. Since they take up most of the universe's space, knowing how voids work is super important for getting the whole story of the universe's history. Plus, we can use voids to check if our ideas about dark matter and dark energy are on the right track. When we talk about the edge of the observable universe, we're talking about the farthest point from us that light has had time to travel since the universe began about 13.8 billion years ago. It's like exploring the very limits of what we can see and know about the universe. Imagine the observable universe as a giant bubble around us with Earth at the center. This bubble has a radius of about 46.5 billion light-years, which might sound strange since the universe is only 13.8 billion years old. But here's the thing. The universe has been stretching over time, kind of like dough rising in the oven. This stretching has carried light from really far away, making the observable universe bigger than you might expect. So this bubble isn't a fixed line in space, but more like a moving frontier. As light from far-off places travels toward us, the bubble expands. But there's a limit to how far we can see. Beyond a certain point, light hasn't had enough time to reach us yet. It's not that the universe stops there, it's just that we can't see beyond that point yet. The idea of the observable universe's edge is closely linked with the inflationary model of the early universe. According to this model, there was a phase of rapid, exponential expansion shortly after the Big Bang. During this period, vast regions of the universe were propelled far beyond what we can currently observe. This expansion greatly contributes to the vastness of the unobservable universe, as these regions are now beyond our observational capabilities. This concept serves as a poignant reminder of the dynamic nature of the universe. Over billions of years, it has been continuously expanding and evolving. Therefore, the edge of the observable universe is not just a physical boundary, but also a temporal one. It marks not only the limit of what we can currently see, but also signifies a point in time beyond which our observations cannot extend. When we gaze into space, we're actually looking back in time. The light we see from the farthest reaches of the universe carries information from its earliest days. This lets us witness the birth of galaxies and the lingering glow of the Big Bang, known as cosmic microwave background radiation. These observations are incredibly important for cosmology, as they help us understand how the universe began, what it's made of, and what its future might hold. At the very edge of what we can see in space, we encounter a frontier of immense discovery and intrigue. This boundary is roughly 46.5 billion light-years away, marking the farthest extent of our cosmic vision and giving us a glimpse into the universe's earliest moments. Here we find clues about the universe's infancy, a time close to the Big Bang itself, revealed through the oldest light that reaches us, the cosmic microwave background radiation. The CMB radiation is like a faint echo of the Big Bang, lingering since the universe was just 380,000 years old and had cooled enough for light to travel freely. Before this time, the universe was a hot, dense soup of particles where light couldn't easily escape. But as the universe expanded and cooled, particles combined to form neutral atoms, allowing light to travel unimpeded. This relic radiation gives us a unique window into the early universe and its evolution over billions of years. The cosmic microwave background radiation we detect today is essentially light that has been stretched out to microwave wavelengths due to the universe's expansion. By observing the CMB, we get a glimpse of the universe in its earliest and most uniform state, showing slight temperature differences that indicate variations in density. These variations were the building blocks for everything we see today: galaxies, stars, and planets. Studying the CMB has been incredibly important in cosmology. It has provided solid evidence supporting the Big Bang theory and has helped us figure out key details about the universe, like how old it is, what it's made of, and how fast it's expanding. But beyond the CMB and the earliest light we can detect, things start to get more speculative. The universe outside of what we can see likely continues on, possibly forever, filled with galaxies, stars, and planets similar to the ones we know. However, since light from these distant regions hasn't reached us yet, we can't directly study or detect them. This idea challenges our understanding of space and time. In cosmology, the edge of what we can see isn't a physical barrier, but a limit set by the speed of light and the age of the universe. As we look farther into space, we're also looking farther back in time. So, the edge of what we can observe represents the earliest moments we can witness, beyond which the universe remains a mystery to us. At this boundary lies the ancient light of the CMB, giving us a direct link to the universe's birth. Beyond that lies a universe full of wonders yet to be explored, shaped by the ongoing expansion of space. The expansion of the universe lies at the core of modern cosmology, causing space itself to stretch and galaxies to move away from each other over time. This phenomenon has a direct impact on how we perceive the universe, affecting both its size and the light traveling through it. As space expands, light from distant galaxies stretches along with it. This stretching process leads to a phenomenon called redshift, where light shifts towards longer, redder wavelengths as it travels towards us. The farther a galaxy is, the more its light is redshifted, making it seem like it's moving away from us faster. This relationship between distance and speed of recession is described by Hubble's law, named after Edwin Hubble, who first noticed this expansion in the 1920s. The expansion of the universe not only alters the light we observe, but also defines the boundaries of what we can see. The observable universe is limited by the cosmic light horizon, the farthest distance from which light has had time to reach us since the universe began. Because the universe has a finite age of approximately 13.8 billion years, there's a limit to how far we can see. While the universe's expansion stretches this horizon, allowing us to see light from farther away, some regions are moving away from us so rapidly that their light will never reach us, placing them beyond our observable universe. This expansion also affects how we will observe the cosmos in the future. As the universe keeps expanding, driven by an enigmatic force called dark energy, galaxies beyond our local group, like the Milky Way and its closest companions, will eventually drift beyond what we can see, reaching a point known as our cosmic horizon. This means their light won't be able to reach us anymore, essentially rendering them invisible and beyond our reach, shrinking our observable universe significantly. Additionally, the ongoing expansion affects the cosmic microwave background, CMB radiation, the oldest light we can detect, which offers a glimpse of the universe just 380,000 years after the Big Bang. As the universe expands, the CMB radiation gets stretched to longer wavelengths, making it cooler and more challenging to detect, gradually fading from our view. One of the most significant contributions of the CMB to cosmology is its role in confirming the Big Bang theory. Before its discovery in 1965 by Arno Penzias and Robert Wilson, there was much debate about how the universe began. The detection of the CMB provided concrete evidence supporting the Big Bang theory, reshaping our understanding of the universe's origins. Moreover, the CMB provides a detailed map of the early universe. The tiny temperature variations within the CMB, as minuscule as 1 part in 100,000, indicate the density differences that existed in the early universe. These differences were the seeds from which all the structures we see today, such as galaxies, clusters, and superclusters, eventually emerged. By examining these subtle variations, cosmologists can deduce how matter and energy were distributed in the early universe, offering insights into the formation and evolution of galaxies across billions of years. Additionally, the cosmic microwave background, CMB, serves as a crucial tool for determining fundamental aspects of the universe, such as its age, shape, and composition. Precise measurements of the CMB have confirmed that the universe is flat on large scales and have provided accurate estimates of its age. Moreover, the CMB provides valuable clues about dark matter and dark energy, two enigmatic components that together make up about 95% of the universe's total mass-energy content. Studying the CMB also delves into the core principles of physics, refining our understanding of the fundamental forces governing the universe. For instance, the subtle patterns and asymmetries observed within the CMB have implications for inflation theory, a leading explanation for the universe's rapid expansion shortly after the Big Bang. However, observing the edge of the observable universe poses significant challenges, stemming from both technological limitations and the laws of physics themselves. These challenges encompass the immense distances involved, the faintness of the signals we're trying to detect, and the intricate interplay of cosmic phenomena that can obscure or distort our observations. The sheer scale of the universe presents a major obstacle, with the edge of the observable universe lying approximately 46.5 billion light-years away from us, a distance light has traveled since the universe's inception, roughly 13.8 billion years ago, factoring in its expansion over time. At immense distances, the light emitted by the earliest stars and galaxies is not only incredibly faint, but also significantly shifted towards longer wavelengths due to the universe's expansion. This phenomenon, called redshift, often pushes the light beyond the visible spectrum into the infrared or even microwave range, requiring highly sensitive instruments to detect these faint signals. Moreover, CMB radiation, which is the lingering glow from the Big Bang and the earliest form of electromagnetic radiation we can observe, presents both opportunities and challenges. While it offers valuable insights into the early universe, it also acts as a sort of cosmic barrier, making it difficult for traditional observation methods to see beyond it. This means that any light or electromagnetic radiation from before this epoch, roughly 380,000 years after the Big Bang, is hidden from our view. Another challenge in observing the universe's edge is the limitations of our current technology. While telescopes, whether ground-based or in space, have become increasingly advanced, they have inherent limitations in their ability to resolve faint and distant objects against the backdrop of the universe. Innovations in telescope technology and the development of new observation methods like gravitational wave astronomy offer promising solutions to these challenges, but they require significant time, investment, and technological breakthroughs. Additionally, the presence of interstellar and intergalactic medium, composed of gas and dust that fills the space between stars and galaxies, can absorb, scatter, and alter light, further complicating observations. These effects can distort the signals we receive, making it crucial to employ sophisticated models and corrections to interpret the data accurately. Lastly, understanding the universe's theoretical framework also presents its own set of challenges. Our understanding of how the cosmos evolves, rooted in principles of general relativity and quantum mechanics, is pushed to its limits when we explore the extreme conditions at the edge of what we can observe. Any anomalies or unexpected discoveries in this frontier could shake up existing theories, prompting the need for new physics to provide explanations. This close connection between observation and theory means that grasping the mysteries of the universe's edge requires not only technological advancements, but also innovative conceptual frameworks. As we venture into the next segment of this documentary, we encounter a puzzling phenomenon: dark matter. Despite being invisible and escaping detection by conventional means, dark matter constitutes about 27% of the universe's total mass energy content. Dark matter, unlike the regular matter we're familiar with, such as stars and planets, doesn't interact with light in any way. This makes it extremely challenging to observe directly. However, we can detect its presence through its gravitational effects on visible matter, radiation, and the overall structure of the universe. The story of dark matter starts with observations of galaxies and galaxy clusters. Back in the 1930s, astronomer Fritz Zwicky studied the Coma galaxy cluster and noticed something peculiar. The visible matter in the galaxies wasn't enough to explain the gravitational force holding them together. The galaxies were moving too fast, suggesting there had to be something else providing additional gravitational pull. Zwicky called this mysterious substance dark matter. More evidence for dark matter came later, in the 1970s, from observations of galaxy rotation curves by Vera Rubin and others. They found that stars in galaxies were orbiting much faster than they should be, based on the gravitational pull of the visible matter alone. Once again, this pointed to the presence of unseen mass, which was necessary to keep the galaxies from flying apart. Dark matter plays a critical role in how the universe forms and changes over time. According to theories of cosmic evolution, dark matter's gravitational pull helped gather regular matter into dense areas, forming galaxies and galaxy clusters. Without dark matter, the universe's structure would be much simpler, and life as we know it might not have been possible. Despite its importance, dark matter remains one of science's biggest mysteries. It doesn't interact with light or other electromagnetic forces, making it invisible. We can only detect it through its gravitational effects on other objects. Scientists are conducting various experiments to directly detect dark matter particles. These experiments often involve highly sensitive detectors placed deep underground to shield them from interference. Understanding what dark matter is made of is a major focus of scientific research. There are several proposed candidates, such as weakly interacting massive particles, axions, and sterile neutrinos, but none have been found yet. The search for dark matter isn't just about identifying a substance. It's also about pushing the boundaries of physics, challenging our understanding of the universe, and redefining our concepts of matter. In our quest to understand dark matter, we're pushing the boundaries of what we know and what our technology can do. This journey connects two seemingly different worlds, the vast cosmos and the tiny realm of particle physics. Figuring out the mystery of dark matter isn't just about finding out what most of the universe is made of. It's also about delving deeper into the fundamental laws that govern everything, giving us insights into space, time, and reality itself. Even though dark matter is invisible and tricky to detect, it leaves behind clues that scientists can use to figure out its presence and importance in shaping the universe. Our journey into understanding dark matter began when astronomer Fritz Zwicky studied the Coma cluster in the 1930s. He noticed that the galaxies within it were moving way too fast for the visible mass to hold them together. This hinted at the existence of a lot of unseen mass, which Zwicky called dark matter. More evidence for dark matter came later, in the 1970s, from Vera Rubin and her colleagues. They looked at how fast stars were moving around the center of galaxies. According to what we know about gravity, stars farther from the center of a galaxy should move slower than those closer in, where most of the visible mass is. But that's not what they found. However, when scientists looked closely, they found something surprising. Stars on the outer edges of galaxies were orbiting at the same speed as those closer to the center. This suggested that there had to be a lot more mass present than what we could see. This unseen mass was exerting extra gravitational pull, keeping those stars moving quickly even at far distances from the center. This was something that visible matter alone couldn't explain. Another crucial piece of evidence for dark matter comes from studying the cosmic microwave background radiation. This radiation is like a leftover glow from the Big Bang. Satellites such as the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck Space Observatory have measured tiny changes in temperature in the CMB. These changes show us how the density of the early universe varied. The patterns and sizes of these changes match up with what models predict if dark matter played a role in shaping the universe's structure. Another way we see evidence for dark matter is through something called gravitational lensing. This happens when the gravity of a big object bends the path of light from something behind it. When we observe this bending of light, we sometimes find that there's no visible object causing it. This tells us that there must be some massive invisible structure there, which we attribute to dark matter. Putting all these pieces together, observations of galaxy motions, the CMB radiation, and gravitational lensing gives us a strong case for the existence of dark matter. Dark matter's role in the universe is like the hidden framework of a building. It's unseen, but crucial for keeping everything together. One of its main jobs is to help galaxies and galaxy clusters form. In the early universe, dark matter's gravity pulled gas and dust together, kick-starting the process of forming stars and galaxies. Without dark matter's gravitational pull, the gas spread out in the early universe wouldn't have come together enough to form the stars, planets, and galaxies we see today. Dark matter also helps explain something odd about how galaxies spin. Usually, stars on the edges of galaxies should move slower than those closer to the center. But that's not what we see. Instead, they all move at similar speeds. Dark matter steps in here, providing extra gravity to keep galaxies from flying apart as they spin. On a bigger scale, dark matter shapes the universe's overall structure, known as the cosmic web. This huge network of galaxies and galaxy clusters is connected by dark matter filaments and separated by voids, forming the backbone of the universe. Dark matter's gravity is responsible for how galaxies bunch together and spread out, creating the intricate patterns we see in space. Without dark matter, the cosmic web wouldn't have its delicate structure, with galaxies clustering together in certain spots. Dark matter also helps with something called gravitational lensing, where the gravity of a big object bends light from something behind it, like a distant galaxy or quasar. Gravitational lensing, a phenomenon where the gravitational pull of massive objects like galaxies bends and magnifies light, serves as a natural telescope. This effect not only confirms the existence of dark matter, but also enables astronomers to map its distribution across the universe. By distorting the light from distant objects, gravitational lensing provides a unique way to study the elusive dark universe. Another intriguing aspect of cosmology is dark energy, a concept that emerged from observations of distant supernovae. In the late 1990s, scientists discovered that these exploding stars appeared fainter than anticipated, suggesting they were farther away than previously thought. This unexpected dimness indicated that rather than slowing down, the universe's expansion was actually accelerating. This accelerated expansion can only be explained by the presence of an enigmatic energy component with a repulsive force, countering gravity's pull and pushing galaxies apart. This mysterious force was termed dark energy. Its true nature remains one of the most profound puzzles in modern science. Unlike dark matter, which clumps together and influences the structure of the universe, dark energy seems to be evenly spread throughout space, exerting its influence uniformly. It doesn't thin out as the universe expands, setting it apart from both regular and dark matter. One prominent theory proposes that dark energy could be an inherent property of space itself, as described by Albert Einstein's cosmological constant. Initially deemed a mistake by Einstein, this term was introduced into his equations of general relativity. According to this theory, empty space isn't truly empty, but possesses its own intrinsic energy. Another perspective suggests that dark energy may be a dynamic field, akin to electromagnetic fields, but with a distinct repulsive characteristic. This field, often referred to as quintessence, could evolve over time, unlike the cosmological constant, which remains constant. While various theoretical models propose different forms of quintessence, there's currently no direct evidence supporting these hypotheses. As we explore the mysterious essence of dark energy, we uncover its crucial role in driving the universe's expansion, a force that propels the cosmos to grow at a rate far beyond previous conceptions. Dark energy constitutes approximately 68% of the universe's total energy content, countering the gravitational pull that tends to draw galaxies and other cosmic structures closer together. Rather than attracting, dark energy exerts a repulsive force, pushing the fabric of the universe apart and causing its expansion to accelerate. This acceleration was initially detected in the late 1990s through observations of distant supernovae. Astronomers had anticipated that these cosmic explosions would reveal a slowing down of the universe's expansion due to the influence of gravity. The recent data we've gathered has uncovered something unexpected. The universe is actually expanding at a faster rate than it did in the past. This discovery strongly suggests the presence of something called dark energy. Unlike regular matter, which tends to clump together forming structures like galaxies, dark energy is spread uniformly throughout the universe. It exerts a repulsive force, pushing things away from each other. This continuous push causes the universe to expand faster over time. The influence of dark energy on the universe's expansion is significant and wide-reaching. It affects the fate of the entire cosmos. If dark energy remains stable or even becomes stronger over time, the universe may keep expanding indefinitely. This would result in a colder and more desolate universe as galaxies move farther apart and eventually stop forming stars. In more extreme scenarios, if dark energy becomes even stronger, it could lead to what's called a big rip. This would mean the repulsive force overwhelms everything, tearing apart galaxies, stars, planets, and even atoms. Understanding how dark energy impacts the universe's expansion isn't just about measuring how fast it's expanding. It also involves piecing together the entire history of the universe. We gather information from various sources, like studying the cosmic microwave background radiation, which is essentially the afterglow of the Big Bang. By examining this and conducting large-scale surveys of galaxies, scientists can map out how the universe has evolved over billions of years. This helps us understand how dark energy's repulsive force has shaped the cosmos. Studying dark energy and its effects on cosmic expansion is a cutting-edge field in cosmology. It challenges our current understanding of physics and calls for new theories to explain its properties and influence. Some theories, like quintessence, suggest that dark energy isn't constant but rather a dynamic field that changes over time, potentially impacting the universe's expansion in different ways. We'll leave it at that. Thank you guys so much for watching yet another SpaceDrift documentary. Be sure to subscribe and like the video for more. And with that being said, take care.